Hello everyone, good afternoon. I am Kornel Lewandowski, and today I will present the solution for masking personal data in medical documents. So enjoy. At first, a few words about me. I am the big data developer and natural language processing specialist, and I work for the Roche company. And this is a pharmaceutical company, and I work in the Global IT Solution Center, which supports the core business, which is pharmacy, from the side of the IT. Okay, so outline of today's presentation is quite short. It's only 3 points. The first one is business justification of the project. The second one is the architecture, high-level architecture overview. And the last one is devoted to the implementation, and this one will be the longest. Okay, so business case. Pharmacy is the very, very crazy business, and we have a lot of external and internal policies regarding to sharing data, sharing data even inside the company, not only outside of them. And all the data containing personal information has to be de-identified. What does it mean? It means that they have to be masked, all the personal data have to be removed or replaced by some placeholders or something like that. Yeah, and some regulators force the pharmaceutical company to do this with all of the data, and this process cannot be performed manually because the number of the documents is pretty high and growing. So we had to implement some automatically solution for solving this task. Okay, in our case, our internal client, let's say, was the medical information part of the company. The medical information is a part of each pharmaceutical company. Have you ever heard about this? Anyone? No? Okay, so medical information is a part which is responsible for supporting all the projects available on the market. And they have to respond all the questions related to the products, to the dosages of medicines, to the clinical trials, results, etc. And they receive a lot of communications from scientists, from physicians, from medical doctors, from even patients, with questions about some dosages, adverse events, etc. And all these questions has to be responded by the medical information part. And they are doing this job very well, but for a little bit more advanced analytic doing all this data, they have to mask all the personal data of these documents because they are not the data scientists, and the batches with all these question, all those inquiries could be really, really helpful and proceed some nice insights from this data. And for sharing the data with the other teams, with the external companies, or just external tools outside our intranet, the data has to be masked. And this was our first implementation we had to do. Yeah, this is the definition of medical inquiry and example of medical inquiry they received. So as you see, it is a lot of personal data on each document. This one is quite short, but a lot of them are a bit longer, but it don't fit on the slide. So I choose this one. Yeah, and as you see, this is the person name, the address, email address, the phone number, and all of them has to be masked. And from there we go to our architecture. The one of our architecture constraints was to integrate this solution for masking the personal data with existing tool for analytics, for medical information textual analysis. This is also the tool they are able to use for do some simple analysis like just hottest topic detection, most frequent words detection, etc. Yeah, and we had to integrate our solution for masking with them. And the solution existing was established as a Hadoop project with usage of MapReduce paradigm. and HDFS data storage and also Oracle data storage. So we had to build a solution which is an additional step between retrieving the data and passing them to the analytics tool. And our data masking solution does not impact on the context of the words in the sentences. When they are masked, they are still the same part of speech, so they can be analyzed by the NLP tools as well as without this masking. Yeah, and this is something that indicates that we have to use some solution which is related with the Hadoop ecosystem with MapReduce paradigm, and we decided to use the Hadoop streaming. Hadoop streaming is a pretty powerful tool which allow us to run the code written in any language, any programming language, as a MapReduce task. And here we use this for write code in Python. To use the Hadoop streaming, your code has to match 3 requirements. The first one is your cluster has to support the programming language you choose. So this is why we choose the Python 2, not Python 3, because our Cloudera instance doesn't support the Python 3 for now. Yeah, and the other 2 requirements is you have to communicate between the workers, between mappers, reducers, data source via standard input and output. And the third requirement is all the data, sent data has to be key value data. And in our case, what you can see on the slide, it is the CSV data when the first column is just the identifier and the other columns as treated just as a value from this key value approach. Okay, so this is the pipeline of our single mapper. Our single mapper, which is dedicated for processing one document at once, is retrieving the data from HDFS, which are previously copied from Oracle database. And in the first step of each mapper, we try to detect the language of the document, because all of the components we use in the further processing are pretty language dependent. Yeah, so the first step is to detect the language, and we also have information about the country from the inquiry comes, because this is also very important information for us, not only language but also country, because we support, for example, the Switzerland, where we have 3 different languages which are used by citizens. Okay, and after detecting the language, we go to the next step. The next step is the finding step. We have a lot of specialized finders, which are responsible for finding just one kind of entity with usage of just one method, and they work independently. So we have 5 or 6 approaches for finding some entities, and each entity is founded by another finder. So we have, I don't know, 20 or 30 independently working finders, and they are trying to find some entities to be masked in completely different ways, and then the results after these finders has to be merged, because some of entities can be overlapping or pretty the same, and this way is pretty good in increasing the recall of our finders, because we find a lot of false positives, but also a lot and pretty all the false positives. So this was this was the most important for us to increasing the recall as high as it is possible with some without worrying about the precision, because for increasing precision we have additional step which we call filters, and in this phase we remove some false positives. Okay, and after this step we mask the data and store them into the reporting database, which is a part of the pipeline from the solution for medical information textual analytics. Okay, so first type of finder we have is pretty simple. We use the regular expressions, which is pretty fast, pretty good. It has very, very well results for well-formatted, well-structured data like email addresses, phone numbers, postal codes, etc. And I think the most if you use the regular expressions. So I have a question for you. What do you think about the regular expression for finding emails? How long it could be? Give the number of characters. 2000. 2000? Any other ideas? Sorry? Couple of lines. Okay, this is our regular expression for finding just emails. It is pretty complicated, but the easiest versions, simplest versions, were not able to find all of the emails you have because users are really, really creative in registering new emails account, and in the real data, this is the only, this is the simplest regular expressions we were able to use in our data to have 100% recall for finding emails. Yeah. So over 400 characters and 11 groups. Okay, so we also use this for finding the phone numbers and postal codes. This situation is simpler. The regular expressions are simpler, but this is additional problem. In each country we support the phone numbers and postal codes has completely different format. For postal code it is completely obvious, but I was very shocked when I tried to use the regular expressions for finding English phone numbers in the German data and in the other languages, because the even length of the phone numbers is pretty different in a lot of European countries. So we have the 9 digits numbers in Germany. Really often they are 10 or 11 digits even. So it was pretty challenging to create the regular expressions for each country, and I worry that if I summarize the length of all of them, it will be longer than the regular expression for emails. Okay, the next approach we took is the approach based on the dictionaries. As a big pharmaceutical company, we have a lot of dictionaries containing the names of hospitals, the names of our competitors, the names of the companies we are co-working constantly. So we decided to use them, and it was pretty good idea because it increased our recall significantly. But we also had few problems with that. The first one was the performance. Matching the dictionaries containing few millions of records with our text was pretty slow. So even for a single document, we had to perform over half of billion matches, and we decided to reorganize our dictionaries and to use the Aho-Korasik algorithm for increase the speed of finding entities. And it was a pretty good idea because it is much faster, but unfortunately it requires a lot of memory and a lot of time to build these structures called the tree or the suffix tree. This I letter is not a typo. This is the name of the structure used in this algorithm. Yeah, so we decide to use this method, and this has also the one more limitation. It supports only the exact matches. So if we have some inflected forms of any words, it doesn't work generally. But in case of the personal information, in case of company names, company addresses, they are also in the very simple form. This is singular for each European language, etc. So we don't worry about this situation. The most challenging situation was with some abbreviations and shortcuts, because we had to unify all our dictionaries, and we had to add a normalization step for document processing to have always the same form for this type of entities, because st.jones it should be completely the same as St. John, etc. So we had to ask some native speakers, some linguists to generate the rules for replacing all this abbreviation and so on into the full forms, and then we were able to use them as is. But it significantly increased the recall and even precision of our solution. So it was really worthwhile to implement this approach. And this is how this suffix tree looks like. Okay, the most sophisticated approach we used in this solution is the named entities recognizer, NER. This is the subtask from natural language processing, which is responsible for using a statistical model or something like that, a machine learning model, to locate and recognize the entities, which can be the person names, locations names, addresses, or time events, or something like that. So this is the pretty thing we needed, but the implementations of NERs were not sufficient for us, and this is only one of additional finder we use, not the only one, because the models are not well trained on the data we have. They are usually trained on the corpora from, for example, newspapers, etc. And this is pretty different things that the emails, but still it is usable and can increase the overall quality of the solution. Yeah, we decided to use the Stanford NER. This is how it works on this inquiry I showed previously. It is able to find three types of, the model we use for English is able to find three types of entities: the person name, location name, and organization name. And here we have some false positives, and yeah, all we wanted to be found it is, but we have some overfinding, some false positives. Why we decided to use the NER from Stanford University? Because they provide the models for the languages we started to work with, so English, German, and Spanish. Unfortunately, they don't support French or Italian, but and we had to train our own models. But we found on the internet some free for access. The corpora are annotated by linguists, and we were able to use them to train our own models. Yeah, and this is also pretty challenging, because the corpora annotation format is not always the same for all the input data, and so we had to put a lot of effort to prepare the format for be suitable to our Stanford NER approach. Yeah, and the training of these models, training of conditional random fields classifier on big amount of data is pretty slow, and on this laptop it took over 20 hours. So, and I done some mistake before teaching this model, and I had to reply this process, and it took me over 1 week to get the model from the well annotated data. Yeah, so this is pretty crazy. Yeah, and our solution is written in Python, but we don't use the Python implementation of this Stanford NER. Why? Because the Python implementation is based on NLTK, and there is a big bug in this library related to the named entity recognition, because NLTK reloads the model really often. I don't know why, and it is pretty slow because the language model can have over 2 gigabytes, and reloading the 2 gigabytes from the hard disk to memory a few times in a minute is pretty slow, and we had to find another solution. Fortunately, the one of solutions proposed by Stanford University is pretty well working. The solution is to run the Java application, the Java Stanford NER, as a web service, and just communicating from the Python code to this web service. The model is loaded only once at start, and it works pretty good and pretty fast. Okay, so the last kind of finders we use is the rule-based finder. After we receive a lot of corpora annotated by our subject matter experts, and after automatically masking a lot of documents, we decide to find some rules which are related to the words order in the documents, and we tried to find after which word, after what word, the entity we would like to find occurs really frequent. And we receive some obvious rules like there, which are pretty common for our emails. But we also retrieve some very variable insights, and they impact us to they enforce us to rewrite some regular expressions we used to be better, to be most suitable to our data. Because yeah, this analysis was pretty fruitful for us. Okay, and after finding the data, after the finders finish their work, we go to the filters phase. In the filters phase, we have we filter the false positives. Why we do this in this phase, not by tuning the models, because this is easier. If we have the models which are ready from the Stanford University or something like that, we don't want to retry them to increase the precision. The recall is satisfying us, and we have some rules for filtering the data which are false positive for us, and we just drop them in this phase. Yeah, here we have the example with 3 entities which are recognized as the person names, and only the one is the correct person name. Do you have any idea why Sabrina is not?
Sabrina was the name of data.
Really close. Sabrina is the name of clinical study. Yeah, so this is, yeah, but good intention. So we have also the dictionary of all clinical studies names, etc., because they are really often named as by English female names, and we have to filter this in this step because we are not able to enforce NER to drop this kind of names in the previous stage. Okay, and after filtering, we merge the entities. It is also a pretty interesting thing we do, because if the finders work completely independently, they can find the same entities in the same places, or some overlapping entities, or something like that. And sometimes we have the situation that in this text, the NER or the other finders found the George Washington as a person name. The second one found the Washington Hospital, and we have to apply the rule for merging these 2 entities. It is pretty obvious because these 2 are overlapping, so we can merge them. And the question is what label we should put. It is the person name, the account name, or something like that. And we had to work a few days with our subject matter expert to prioritize the type of entities and to create some rules to decide which entity type is more general or something like that, and which one should be applied. And when we have the data find, filtered, and merged the entities, we are able to mask the data. And this step is pretty simple because we are just replacing the found entities by some placeholders. For now, we are supporting the 5 types of entities: person name, account name or organization name, post address, email address, and phone numbers. These 5 are required by some external regulations for pharmaceutical companies. So this is enough for us, and yeah, and that's it. Our future plans: we would like to support some East Asian languages. The Chinese is the next one. For now, we support 7 languages, but each of them are European languages. Yeah, and the other step in the future we would like to do is to support the mixed language documents because we have a few documents which are, for example, the emails written in German, then forwarded to someone who is English speaker, and the message in the forward one is in English. So we have the document in 2 different languages. And if we recognize this one as a German, the whole document is processed by German pipeline, and the data, the NER or any other language dependent finders are doing a lot of mistakes for the data written in English, in the English part. So we would like to rewrite it a little bit to be not the document-oriented, but maybe sentence-oriented or something like that to proceed this better. Okay, so that's it from my side. Thank you for your attention. I hope you enjoyed this presentation.
Thank you very much. And do you have any questions, maybe?
Thank you for an interesting presentation. And do you support Polish language? And are you planning to provide a service, maybe the cloud-based service, for the process that you have presented?
No, because this is related to our company regulations. We are the pharmaceutical company, and the regulations from the external law are really restrictive for us, and we are not able to do this as a service. And the first question of you is if we support the Polish language. No, we don't, because we don't have a lot of the documents written in Polish, and even the medical information units we implemented this solution for are sometimes translating all of the communication coming to them to the English, and this is the solution for English enough for them. For example, in Greece, they translate all the inquiries from Greece to English.
How do you resolve conflicts like this dictionary entry, Sabrina, and you should not mask it, and there's maybe a woman named Sabrina Grzdyl and you should mask it? So how do you resolve these type of conflicts?
Okay, so in this situation we just leave the name, because the single person name is not the personal data. The personal data is if you are able to recognize the particular people by getting this data, and the single female name is not, because there could be a lot of Sabrinas in the company. So this is not a big deal for us.
Thank you for the presentation. It was very, very good. You were saying, I forgot the question.
Yeah, thanks as well. Very interesting. I have a question about the label set that you use. Because we had a similar project detecting PII and PHI, but from the security perspective. But what we found out is that these, if I saw correctly, use like person name and location and things like this. They didn't really apply very well. Like location is maybe Poland, but you really want to mask the street address, not just the Poland part. So what we ended up doing is we had to create our own labels and then annotate the data and create our own entities basically. So my question is, was it enough for you, these generic models with the generic labels, or did you do the same thing? Something else?
Okay, the labels we have are requested by the HAPAA regulatory. So these five type of entities are has to be masked in all documents in pharmaceutical and medical companies, and these five labels are pretty enough for us, because if we would like to leave some information like the country or something like that, we just add the additional filter. This is the way we handle it. So if we would like to mask the street name or home number or something like that, we do this. And if we have the name of country like Poland, Germany or something like that, we leave it if it is in our dictionaries.
If there's no more questions, I would like to invite you for a lunch break.